You are listening to Reactive Programming Demystified, a hands-on guide to RxJS. Like and subscribe to keep up to date on our latest audiobooks. Reactive Programming Demystified, a hands-on guide to RxJS. Chapter 1, The Reactive Paradigm Shift. The Reactive Paradigm Shift. The modern web application is a dynamic, interconnected beast. Think about it. As you scroll through a social media feed, new content loads seamlessly. When you type into a search bar, suggestions appear almost instantly. Live dashboards update in real time. Buttons respond to clicks, network requests fetch data, and animations play smoothly, all happening concurrently, often influencing each other. This constant interplay of events and data over time forms the backbone of engaging user experiences. But behind the scenes, managing this symphony of asynchronous operations can feel less like a well-orchestrated performance and more like a chaotic orchestra without a conductor. If you've ever found yourself wrestling with deeply nested callbacks, struggling to cancel an in-flight network request, or trying to manage complex state changes across different parts of your application, you've experienced the asynchronous chaos firsthand. For years, JavaScript developers have relied on patterns like callbacks, and more recently, promises and the async await syntax, to tame this chaos. While these tools brought significant improvements over earlier, more manual approaches, they still fall short when dealing with certain types of asynchronous problems, especially those involving continuous streams of data or interdependent events. This is precisely where reactive programming, and specifically RxJS, steps in. What is reactive programming? At its heart, reactive programming is about programming with asynchronous data streams. Imagine data, events, or state changes not as isolated occurrences, but as continuous flows, like water in a river. Reactive programming provides a set of tools and a mindset to elegantly manage these flows. To grasp this, it's helpful to understand the distinction between two fundamental models of data interaction. The pull model. This is what you're likely most familiar with. When you call a function, it returns a value. When you iterate over an array with a for loop, you pull each item as you need it. Functions and iterators are examples of a pull system. The consumer decides when to request data. Promises, to a degree, also operate in a pull fashion. You define a handler that pulls a resolved value when it's ready. The push model. In contrast, the push model involves a producer that pushes data to a consumer when it's ready, without the consumer explicitly requesting it. Think of an event listener on a button. You don't continually ask the button if it's been clicked. The button pushes a click event to your registered listener when it occurs. Similarly, a real-time chat application pushes new messages to connected clients as they arrive. This push-based approach is fundamental to reactive systems. Reactive programming thrives on this push model. It treats everything, UI events, network responses, variable changes, even simple asynchronous operations, as a stream of data that can be observed. You react to these streams by subscribing to them, transforming them, combining them, and directing their flow. Instead of imperative code that tells the computer how to do something step by step, reactive code tends to be more declarative, describing what should happen to the data as it flows through the system. Why reactive programming? Problems solved. So, how does this push-based, stream-oriented approach solve the asynchronous challenges developers face? Escaping callback hell and nested complexity. We've all seen it. A pyramid of nested function calls, each dependent on the completion of the previous one. While promises and async await flatten this structure, complex chains of dependent or conditional async operations can still be difficult to read and maintain. Reactive programming allows you to express these sequences in a flat, readable pipeline of operations. For example, instead of writing, do something async data 1, result 1 equals. Do another thing async result 1, result 2 equals. Do a third thing async result 2, final result equals. And so on. You might instead describe a flow that transforms data step by step, looking more like stream of data 1. Piped, transform 1, an operator that calls do something async. Transform 2, an operator that calls do another thing async. Transform 3, an operator that calls do a third thing async. Subscribe, final result equals. Handle result. This linear, pipeline structure significantly improves readability and maintainability. Managing asynchronous data flow and state changes over time. Modern applications are often characterized by events happening continuously, mouse movements, keyboard input, real-time data from a server. Traditional promises are one and done. They resolve or reject a single time. They aren't designed for handling a series of events over time. Reactive programming, with its focus on streams, is perfectly suited for these scenarios, allowing you to model state and handle complex event sequences gracefully, handling concurrency and race conditions more predictably. What happens if a user clicks a button multiple times when an expensive network request is in flight? Do you send multiple requests, or just the first one, or only the latest one? What if multiple data sources need to be combined before appearing on screen? Reactive programming provides powerful operators to manage these concurrency scenarios, allowing you to easily cancel ongoing operations, debounce rapid inputs, or combine multiple data streams reliably, improving code readability and composability with a declarative style. Reactive code often describes what you want to achieve with a stream rather than how to achieve it. This declarative style can make the code easier to reason about, especially for complex asynchronous interactions. Operators are like Lego bricks that can be combined and reused, promoting modularity and composability. A brief history, from Rx to RxJS. The concepts of reactive programming didn't just appear out of thin air. They originated at Microsoft, where the Reactive Extensions, Rx, library was developed for the .NET framework in the late 2000s. Led by Eric Major, the goal was to provide a unified way to compose asynchronous and event-based programs using observable sequences. Rx proved to be incredibly powerful and influential. Soon, ports began to appear in other programming languages. RxJS is the JavaScript implementation of reactive extensions. It has evolved significantly over the years, with various major versions refining its API and performance. Modern RxJS, version 6 and beyond, emphasizes a pipeable operator syntax that promotes tree shaking, removing unused code from your application's final bundle, and functional composition, making it more efficient and idiomatic for JavaScript development. Today, RxJS is a robust, well-maintained library that forms the backbone of many popular JavaScript frameworks, most notably Angular. The pillars of RxJS. A high-level overview. To speak the language of RxJS, you need to understand its core building blocks. Don't worry if these sound abstract now, we'll dedicate entire chapters to each. For now, think of them as the primary characters in our reactive story. Observables. This is the core concept. An observable represents the stream itself, a collection of values or events that arrive over time. It's the blueprint for how data will be produced. Observers. These are the consumers. An observer is an object that subscribes to an observable to receive the values it emits. Observers know how to handle the next value, error, and completion of the stream. Operators. These are pure functions that allow you to transform, filter, combine, and manipulate observables. Operators are like the tools in an assembly line, each performing a specific job on the data flowing through the stream. For example, a map operator might change the format of each item in the stream, while a filter operator might only let certain items pass through. Subscription. When an observer subscribes to an observable, a subscription object is returned. This object represents the active execution of the observable and is crucial for managing resources and, most importantly, stopping the flow of data when it's no longer needed, unsubscribing. Subjects. These are special types of observables that can also act as observers. This dual nature allows them to multicast, meaning they can broadcast values to multiple observers simultaneously. They're often used for communication between different parts of an application or for managing shared state. Schedulers. While less frequently interacted with directly in day-to-day coding, schedulers are vital for advanced control over when and where observable notifications are delivered. They manage concurrency and help control the execution context of asynchronous operations, when to reach for RxJS and when not to. RxJS is a powerful tool, but like any tool, it's best applied to the problems it's designed to solve. When to consider RxJS. UI event handling, managing user interactions like clicks, key presses, mouse movements, form input. If your application heavily relies on dynamic UI interaction, RxJS can make these flows incredibly clean. Reactive data flows, processing real-time data from WebSockets, server-sent events, or complex asynchronous workflows where data continuously updates. State management. Many state management libraries and patterns leverage RxJS because behavior subject, a type of subject, is perfect for holding and emitting current state. Cancellation and rate limiting. For scenarios like a type-ahead search where you want to cancel previous, slower requests if the user types faster, or debounce/throttle rapid events. Complex asynchronous coordination. When you need to combine results from multiple asynchronous operations, handle errors gracefully, or retry failed requests strategically. When simpler alternatives might suffice. Single, one-off asynchronous operations. If you just need to fetch data from an API once and display it, a simple promise or a sync await might be perfectly sufficient and less overhead than introducing RxJS. Basic event handling. For a single button click that performs a straightforward action, a traditional event listener is often clearer. Small, non-interactive scripts. In a simple script where there isn't a continuous flow of events or complex interdependencies, RxJS might add unnecessary complexity. It's not an either-or choice. Rather, it's about choosing the right tool for the job. Often, RxJS seamlessly coexists with promises and a sync await in the same application. Getting started. Installation and first steps. To begin using RxJS, you'll need a JavaScript development environment and a package manager like npm or yarn. The easiest way to install RxJS in your project is via npm. npm install RxJS. Once installed, you can import functions and operators into your JavaScript files. Let's imagine a very simple Hello World example in RxJS. We want an observable that emits the numbers 1, 2, and 3, and then completes. We will then subscribe to it and print those numbers to our console. First, we would import the ofCreation function from the RxJS library. This function helps us quickly create an observable from a list of items. Next, we would define our observable by calling of and passing it our numbers, 1, 2, and 3. This creates an observable blueprint. Finally, we would tell our observable to start producing values by calling its subscribe method. Inside subscribe, we provide a function to handle each next value that comes out of the stream. We could also add functions to handle any error that occurs or when the stream completes. So when our example runs, it prints value 1, then value 2, then value 3 to the console, and then it prints done as the stream signifies its completion. While this example is basic, it illustrates the core flow, an observable producing values and an observer consuming them. We've conceptually walked through this first example to minimize raw code blocks in this book. For a complete code example that you can run and experiment with, you can refer to the accompanying online repository for this book. There, you'll find executable snippets for almost every concept we discuss, allowing you to tinker and see the reactive principles in action. Chapter Summary: Embracing the Stream. In this chapter, we've set the stage for our deep dive into reactive programming with RxJS. We've identified the challenges of traditional asynchronous patterns and introduced the conceptual shift towards thinking in terms of asynchronous data streams. You now understand that reactive programming empowers you to handle complex, continuous event flows with greater clarity, composability, and predictability. We also briefly touched upon the historical context of RxJS and met its core pillars: observables, observers, operators, subscriptions, subjects, and schedulers. With this foundational understanding, we are now ready to journey into the heart of RxJS. In the next chapter, we'll take a closer look at JavaScript's existing asynchronous landscape, further highlighting the unique problems RxJS is designed to solve. Chapter 2: JavaScript's Asynchronous Landscape. Introduction: Building Blocks of Async.js. Before we fully immerse ourselves in the world of reactive programming, it's imperative to take a step back and understand the landscape of asynchronous operations in JavaScript. JavaScript is inherently single-threaded, meaning it executes one operation at a time. However, to prevent user interfaces from freezing or web pages from becoming unresponsive while waiting for long-running tasks like network requests or file I/O, JavaScript employs an event loop and various asynchronous mechanisms. Familiarity with these existing mechanisms, callbacks, promises, and async await, is crucial not only because they form the historical progression of asynchronous JavaScript, but also because they help highlight why RxJS is needed and the specific gaps it fills. Many real-world applications still use a mix of these technologies, and understanding their strengths and weaknesses will clarify where RxJS truly shines. Callbacks. The original way. In the early days of JavaScript, callbacks were the primary mechanism for handling asynchronous operations. A callback is simply a function that is passed as an argument to another function, intended to be executed after the other function has completed its task. Consider a simple set timeout or an event listener. Document get element by ID my button. Add event listener, click, function. Console log, button clicked. This is the callback function. Here, the anonymous function is a callback that will be invoked by the browser's event system whenever the button is clicked. Similarly, when fetching data from a server, you'd typically provide a callback to be executed once the data arrives. Advantages of callbacks: simple and direct. For straightforward, single-level asynchronous operations, callbacks are easy to understand and implement. Widespread use. They are deeply embedded in the browser's web APIs, DOM events, set timeout, XML HTTP request, and Node.js file system networking. Disadvantages of callbacks. While simple for single tasks, callbacks quickly lead to problems when operations become sequential or dependent on each other, giving rise to what's infamously known as callback hell or the pyramid of doom. Imagine a scenario where you need to fetch user data, then use the user's ID to fetch their posts. Then, for each post, fetch its comments. Using callbacks, this might look something like this. This code is illustrative and not runnable without mock functions. Fetch user data, user ID, function, user data. Console log, user data fetched, user data. Fetch user posts, user data ID, function, posts. Console log, user posts fetched, posts, posts for each function post. Fetch post comments, post ID, function, comments. Console log, comments for post posted, comments. What if we need to do something else here? More nesting, function error, error callback for comments. Console error, error fetching comments, error, function error, error callback for posts. Console error, error fetching posts, error, function error, error callback for user data. Console error, error fetching user data, error. As you can see, the code becomes deeply indented and difficult to read, track, and maintain. Error handling also becomes cumbersome, as each nested callback typically requires its own error handler, leading to repetitive code. Additionally, it's hard to pass results between deeply nested callbacks without resorting to complex variable scoping. Promises, a structured improvement. To address the shortcomings of callbacks, ECMAScript 2015 ES6 introduced promises. A promise is an object that represents the eventual completion or failure of an asynchronous operation and its resulting value. Instead of immediately returning the final value, an asynchronous function returns a promise. This promise then acts as a placeholder for the result. A promise can be in one of three states: pending, the initial state, neither fulfilled nor rejected. Fulfilled, resolve, the operation completed successfully and the promise has a resulting value. Rejected, reject, the operation failed and the promise has a reason for the failure and error. You attach handlers to a promise using its then and catch methods. This allows for a much flatter and more readable chain of asynchronous operations compared to nested callbacks. Revisiting our previous example with promises, this code is illustrative and not runnable without mock functions. Fetch user data, user ID. Then, user data equals. Console log, user data fetched, user data. Return fetch user posts, user data ID. Return a new promise. Then posts equals. Console log, user posts fetched, posts. Map each post to a promise that fetches its comments. Const comment promises equals posts map. Post equals fetch post comments, post ID. Return promise all, comment promises. Wait for all comment fetches to complete. Then comments array equals. Comments array for each, comments index equals. Console log comments for post index, comments. Catch error equals. Single catch block handles errors anywhere in the chain. Console error, an error occurred. Error. This promise-based version is significantly more readable. Error handling is centralized with a single catch block, which is a major advantage. Promises also offer utilities like promise all, wait for all promises to resolve, and promise race. Resolve reject as soon as one promise resolves rejects. Key limitations of promises, especially in the context of RxJS. Despite their significant improvements, promises have certain limitations that highlight the specific strengths of RxJS. Single value emission. A promise can only resolve or reject once. It's designed for a single, discrete asynchronous result, e.g., one API response. It cannot handle a sequence of values over time, like continuous user input, mouse clicks, key presses, or real-time data streams from WebSockets. Not cancelable. Once a promise is initiated, there's no built-in way to cancel it. This can be problematic in scenarios like a type-ahead search, where you want to cancel previous, outdated network requests if the user keeps typing. Hot by nature. A promise executes as soon as it's defined. If you create a promise that makes an HTTP request, that request will be sent immediately, regardless of whether anything is then to it. You cannot make a promise lazy. No built-in retry mechanism. Promises don't natively offer a way to easily retry a failed operation a certain number of times or with a delay. Async await. Synchronous-looking async code. Introduced in ECMAScript 2017, async await is syntactic sugar built on top of promises. It allows you to write asynchronous code that looks more like synchronous code, making it even more readable for sequential operations. An async function implicitly returns a promise. The await keyword pauses the execution of an async function until the promise it's waiting for resolves. Our example, rewritten with async await. This code is illustrative and not runnable without mock functions. Async function fetch user information, user ID. Try, const user data equals await fetch user data, user ID. Console log user data fetched, user data. Const posts equals await fetch user posts, user date ID. Console log user posts fetched, posts. Fetch comments for all posts concurrently. Const comment promises equals posts map, post equals fetch post comments, post ID. Const comments array equals await promise all, comment promises. Comments array for each, comments, index equals. Console log comments for post index, comments, catch error. Console error, an error occurred, error. Call the async function. Fetch user information, some user ID. The async await syntax further improves readability for sequential asynchronous operations, especially when dealing with multiple await calls that depend on previous results. Error handling is managed with standard try ... catch blocks, familiar from synchronous code. However, async await inherits the fundamental limitations of promises. It's still designed for a single, eventual result. You cannot await a continuous stream of values. It does not provide a cancellation mechanism for the underlying promise. The awaited operation is still hot and begins execution immediately. The gap RxJS fills, beyond one-off asynchronicity. So, with callbacks, promises, and async await at our disposal, when exactly do we need RxJS? The answer lies in the fundamental difference between discrete, one-time asynchronous operations and continuous, multi-value asynchronous streams or events. Promises and async await excel at handling a single future value. Fetch this data, then process it once. They are perfect for scenarios where the asynchronous task produces exactly one outcome. RxJS excels at handling situations where you have a stream of 0, 1, or many values arriving over time. It's designed for reactivity. Consider these scenarios where promises and async await become cumbersome or inadequate. User input streams. Imagine an autocomplete search bar. As the user types, you need to capture every keypress event. Wait a short time after the last keypress debounce to avoid excessive requests. Only perform the search if the text has changed. Cancel any pending old search requests if the user types something new. Handle the search results as they arrive. Promises would require a lot of manual state management, timers, and cancellation logic. RxJS handles this elegantly with a few operators. Drag and drop implementations. This involves a sequence of mouse events: mouse down, mouse move, many times, and mouse up. You need to react to all these events in a coordinated fashion. Real-time data. If you have a WebSocket connection continuously pushing new data, e.g., stock prices, chat messages, promises cannot natively represent this ongoing stream. You'd be back to handling callbacks or event emitters manually. Complex event coordination. When values from multiple independent sources need to be combined or processed together, e.g., combine the latest user input with the latest data from a server and the current time to perform a calculation. In essence, promises are about an asynchronous value that will be available in the future. Observables, and thus RxJS, are about a stream of asynchronous values that may be available in the future. Over time, RxJS provides a rich set of operators and a powerful conceptual model that allows you to manage these dynamic, continuous streams of data and events with immense power and precision. It brings a functional, declarative approach to asynchronous programming, enabling you to compose complex asynchronous logic in a way that is often more concise, readable, and maintainable than traditional methods. Chapter Summary. Paving the way for reactive. We've reviewed the evolution of asynchronous JavaScript, from the foundational callbacks to the widely adopted promises and async await. While each step brought significant improvements, they remain primarily focused on handling single, eventual asynchronous results. This limitation creates a significant gap when dealing with continuous streams of events, multiple values over time, or complex interdependencies between asynchronous operations. In the next chapter, we will dive deeper into the very heart of RxJS, the observable asterisk. We'll learn how this fundamental concept finally provides the elegant solution for managing these dynamic, multi-valued asynchronous streams that JavaScript's traditional tools struggle with. Chapter 3, Introducing Observables, the core of RxJS. Introduction, the stream concept in detail. In the previous chapter, we explored JavaScript's asynchronous past and present, identifying the inherent limitations of promises and async await when faced with continuous, multi-valued asynchronous operations. We hinted that observables are the key to unlocking this next level of asynchronous programming. Now, it's time to dive deep into this foundational concept, which serves as the very backbone of RxJS. If you understand observables, you're more than halfway to understanding RxJS. Get ready to shift your perspective and truly embrace the stream concept. What is an observable? An observable in RxJS represents a source of future values or events. Conceptually, you can think of an observable as a stream, a sequence of items, values, messages, or events that arrive asynchronously over time. Think of it like subscribing to a newsletter. The newsletter publisher is the observable. They are the source of content. You, the subscriber, are the observer. You want to receive the content. By signing up, you create a subscription. Each email you receive is a value emitted by the observable. If the newsletter decides to stop publishing, it completes, and you stop receiving emails. If the newsletter encounters a major problem, e.g., mail server crashes, it errors out, and you stop receiving emails. More formally, an observable is a function that takes an observer as an argument and returns a subscription. When the observable is run, i.e., subscribed to, it executes this function, which then pushes values to the provided observer over time. The observable lifecycle. Every observable follows a predictable lifecycle, governed by 3 types of notifications that can be sent to an observer. Next, value. This notification is sent whenever a new value or event becomes available in the stream. An observable can emit 0, 1, or many next notifications. Error. This notification is sent if an error occurs within the observable's execution. Once an error notification is sent, the observable terminates and will not emit any further next or complete notifications. This behavior is crucial for managing application state and ensuring predictability. Once a stream is broken, it stays broken. complete. This notification is sent when the observable has finished emitting values and will not emit any more next or error notifications. After complete is sent, the observable terminates. An observable completes either by sending an error notification or a complete notification. It will then stop producing values and free up any resources it was using. Creating observables, the foundation. While you typically use a handful of powerful operators to create observables, understanding how to construct one from scratch, the low-level approach, helps cement your understanding of how they fundamentally work. New observable, the low-level approach. This is the most primitive way to create an observable. You pass a function to the observable constructor. This function, sometimes called the subscribe function, receives an observer object as its argument. This observer object has the next, error, and complete methods that you call to push notifications. Let's illustrate with a conceptual example. This is a conceptual explanation. Full code for the book is in external repo. We create an observable that will simulate data fetching. Const myObservable equals new observable, observer equals 1. Simulate data arrival after delay. Set timeout equals observer next, first piece of data. Emit a value. 1000. 2. Simulate another piece of data later. Set timeout equals observer next, second piece of data. 2000. 3. Simulate completion. Set timeout equals observer.complete, signal that the stream is finished. 3000. 4. Optional, return a cleanup function. This function runs when the observer unsubscribes or when the observable completes or errors. Return equals console log observable teardown cleanup logic executed. For example, clear a timeout, close a WebSocket, etc. When you subscribe to my observable, the function inside new observable executes. It calls observer next to push values and observer.complete to signal the end. The cleanup function is critical for resources that need explicit closing, like WebSockets or interval timers. Static creation operators, the factory methods. While new observable gives you fine-grained control, it's rarely used directly in day-to-day RxJS coding. Instead, you'll rely on a rich set of static creation operators, also called factory methods. These are functions that return new observables, abstracting away the low-level details. They are imported directly from the RxJS library. Here are some of the most commonly used ones. Args creates an observable that emits a sequence of values you provide, one after another, and then immediately completes. It's often used for synchronous data. Conceptual example of hello, world, it would emit hello, then world, then, and then complete. From input, creates an observable from various JavaScript primitives, including arrays. Emits each item in the array. Promises, emits the resolved value of the promise, then completes. If the promise rejects, the observable errors. This is a common way to convert a promise into an observable. Iterables. Emits each item from any iterable like set, map, string. Conceptual example, from 10, 20, 30, would emit 10, then 20, then 30, then complete. Interval period. Creates an observable that emits sequential numbers, 0, 1, 2, at a specified interval of milliseconds. This observable emits indefinitely. It does not complete unless manually instructed to. Conceptual example. Interval 1000 would emit 0 after 1 second, 1 after 2 seconds, 2 after 3 seconds, and so on, never completing on its own. Timer, due time period. Creates an observable that, after an initial due time delay, either emits a single value, 0, and then completes, if only due time is provided. Emits sequential numbers at a specified period, if both due time and period are provided, similar to interval. Conceptual example. Timer 2000 waits 2 seconds, emits 0, then completes. Timer 1500 waits 1 second, emits 0, then emits 1 after 1.5 seconds, 2 after 2 seconds, and so on. From event, target, event name. Creates an observable that emits values whenever a specific DOM event occurs on a given target. This is incredibly powerful for handling user interactions in a reactive way. Conceptual example. From event document get element by ID my button. Click would emit a DOM click event object every time the button is clicked. This stream can conceptually go on forever as long as the button exists. Hot versus cold observables, a critical distinction. This is one of the most important concepts to grasp when starting with RxJS, as it directly impacts how your observables behave and consume resources. Cold observables unicast by default. A cold observable starts its execution, or its work, only when somebody subscribes to it. Crucially, each new subscriber gets its own independent execution of the observable. They don't share the work with other subscribers. Analogy: think of a movie you rent. Each time someone rents the movie, they get their own copy and start watching it from the beginning. They don't affect anyone else's viewing experience. Examples: most observables created with new observable, of, from, interval, timer, are cold by default. If two observers subscribe to the same interval, 1000 observable, they will each receive their own independent sequence of numbers, starting from 0 at their own 1-second intervals. This means two separate setinterval calls are happening behind the scenes. Implication: be mindful of resource duplication. If a cold observable performs an expensive operation, like an HTTP request, each subscription will trigger that operation again. Hot observables multicast. A hot observable's execution is already running and producing values, regardless of whether there are any subscribers. Subscribers that come online later will receive values starting from the point of their subscription, or in some cases, the latest value, but they won't trigger a new execution. Instead, they share the single, ongoing execution. Analogy: think of a live radio broadcast. It's broadcasting whether anyone is listening or not. If you tune in, you only hear what's playing at that moment. You don't get to restart the show from the beginning. Examples: DOM events from event are inherently hot. When you attach two event listeners to the same button, they both listen to the same stream of clicks. They don't each trigger a separate button click event. WebSockets are another example. The connection is open, and messages are being received irrespective of how many parts of your application are listening. Implication: hot observables are efficient for shared resources and ensure consistency among listeners. Understanding whether an observable is hot or cold, or how to make a cold observable hot, using subjects or multicasting operators like share, which we'll cover in Chapter 8, is fundamental to optimizing resource usage and managing your application's data flow effectively. The laziness of observables, execution on demand. One of the most powerful characteristics of observables, especially cold ones, is their laziness. An observable will not start producing values until an observer explicitly subscribes to it. This is a critical difference from promises. When you define a promise, the function you pass to its constructor executes immediately. Conceptual difference. Promise executes immediately upon definition. Const my promise equals new promise, resolve equals. Console log promise function executed immediately, resolve promise resolved. Console log after promise definition. This logs before promise function executed. Observable does not execute until subscribed to. Const my lazy observable equals new observable, observer equals. Console log observable function executed only upon subscription. Observer next observable value, observer.complete. Console log after observable definition. This logs before observable function executed. Note: if you run this conceptual code with actual console log statements, you will see promise function executed immediately, before, after promise definition, while observable function executed will only appear after my lazy observable subscribe is called. This laziness provides immense flexibility and efficiency. Resource efficiency. Resources are only consumed when they are actually needed. An observable representing a network request won't trigger the request until something wants its data. Composable pipelines. You can define complex chains of operations using operators, which we'll cover later, without anything actually happening. The entire pipeline springs to life only when you subscribe to its final output. This allows for powerful, descriptive, and reusable data flow blueprints. Chapter summary: your first step into the stream. In this chapter, we've firmly established the observable as the cornerstone of RxJS. You now understand that an observable represents a stream of values over time. capable of pushing next values, terminating with an error, or simply completing. We explored how to create observables, both at a low level using new observable, and more practically, using static creation operators like of, from, interval, timer, and from event. Crucially, we've differentiated between cold and hot observables, a distinction vital for understanding execution models and resource management. And finally, we highlighted the inherent laziness of observables, emphasizing that they only perform work when an observer subscribes. But an observable is only half the story. It produces values. In the next chapter, we'll shift our focus to the other side of the equation, the observer, which consumes these values, and the subscription, which manages the active connection to the stream. Chapter 4, The Observer and the Subscription, Listening to the Stream. Introduction, the consumers of the stream. In the previous chapter, we introduced the observable as the producer of asynchronous data streams, the eloquent storyteller. But a story, no matter how compelling, requires a listener. In RxJS, that listener is the observer. And once the observer begins listening, a subscription is formed, which serves as our means of controlling and eventually ending that listening process. Understanding the observer and subscription is crucial for actively engaging with your reactive streams, ensuring you receive the data you expect, handle errors appropriately, and, most importantly, manage resources effectively to prevent memory leaks and unexpected behavior. The observer, the listener object. An observer in RxJS is simply an object that defines how to react to the notifications sent by an observable. As we learned, an observable can send 3 types of notifications: next, error, and complete. Correspondingly, an observer is an object with 3 optional methods, each designed to handle one of these notifications. Next, value. This method is called by the observable every time it emits a new value. This is where you typically process the data coming from the stream. It can be called 0, 1, or many times. Error, err. This method is called if an error occurs within the observable's execution. When error is called, the observable terminates, and no further next or complete notifications will be sent. This method receives the error object as its argument. Complete. This method is called when the observable has finished emitting all its values and has successfully completed its life cycle. It signals that no more next or error notifications will be sent. Like error, when complete is called, the observable terminates. You don't typically create an observer directly like new observer. Instead, you implicitly define it when you subscribe to an observable. The subscribe method, activating the stream. To initiate an observable's execution and start receiving values, you call it subscribe method. When you call subscribe, you are providing the observable with the observer or functions that will act as the observer's methods that it should send notifications to. There are a few common ways to use the subscribe method. Passing an observer object. This is the most explicit and often clearest way, especially when you need to handle all 3 notification types. / conceptual usage, full code in external repo. Const my observable equals of 1, 2, 3. Emits 1, 2, 3 then completes. Const my observer. Next, value equals console log received. Value. Error der console error. Complete equals console log stream completed. To my observable subscribe my observer. Expected output. Received 1. Received 2. Received 3. Stream completed, passing positional arguments, shorthand. For convenience, you can pass up to 3 functions directly to subscribe, which RxJS then internally maps to the next, error, and complete methods of an observer. / conceptual usage, full code in external repo. Const my observable equals of alpha, beta, my observable subscribe. Value equals console log next. Value, next handler. Console error. Error handler. Equals console log completed, complete handler. Expected output, next, alpha. Next, beta. Completed. If you only care about next values, you can just pass the first argument. My observable subscribe, value equals console log value. Expected output, alpha, beta. Completes silently, as no complete handler provided. It's common practice to provide at least a next handler. For production applications, always consider providing an error handler. Otherwise, unhandled errors in your observable chains might propagate up and potentially crash your application or go unnoticed. The subscription object, managing the stream's life. When you call subscribe on an observable, it doesn't just start the data flow. It returns a subscription object. This subscription object is your handle to the ongoing execution of the observable. It's an incredibly important tool, primarily for one reason: unsubscribe. The unsubscribe method. Resource management. The unsubscribe method cleanly tears down the active connection between the observable and its observer. When called, the observer will no longer receive next, error, or complete notifications from that specific observable execution. The observable's internal cleanup logic, the return function from new observable that we saw in Chapter 3, is executed, releasing any resources that were allocated, e.g., clearing setinterval timers, closing network connections. Why is unsubscribe so important? Preventing memory leaks. If an observable is continuously emitting values, like interval or from event, for a button click, and you navigate away from the component or page that subscribed to it, the observable will continue to run in the background. Without unsubscribe, the observer, and thus the component's context, would remain alive in memory, leading to a memory leak. Controlling unwanted side effects. Imagine an observable that triggers an HTTP request every second. If you don't unsubscribe, these requests will continue even if the user has left the page, wasting resources and potentially causing unexpected behavior. Predictable behavior. Explicitly managing subscriptions ensures your application behaves predictably, starting and stopping data flows precisely when needed. When to unsubscribe, you should always unsubscribe from observables that are long-lived or potentially infinite, like those created with interval, from event, or WebSocket connections, when the component or context that subscribed to them is destroyed or no longer needs the data. /conceptual usage, full code in external repo. Import interval from RxJS, const source $= interval 1000, emits 0, 1, 2. Every second, console log starting subscription, const subscription equals source $, subscribe value, console log value, after 5 seconds manually unsubscribe. Set timeout equals subscription unsubscribe, console log subscription unsubscribed, 5500, expected output, value 0 after 1s, value 1 after 2s, value 2 after 3s, value 3 after 4s, value 4 after 5s. Subscription unsubscribed. No more values will be logged. For observables that naturally complete, e.g., of, from, an array, or an HTTP request that successfully finishes, you typically don't need to explicitly call unsubscribe, as RxJS handles the cleanup automatically when complete or error is called. Subscription add, grouping subscriptions for cleanup. When your application has many observables, managing individual subscription objects can become cumbersome. The subscription object provides an add method that allows you to group multiple subscriptions together. When you unsubscribe from the parent subscription, all child subscriptions added to it will also be unsubscribed. /conceptual usage, full code in external repo. Import interval from event from RxJS. Const main subscription equals new subscription. Subscribe to a click event. Const clicksub equals from event document, click, subscribe, equals. Console log document clicked. Main subscription add click sub. Add click subscription to main. Subscribe to an interval. Const interval sub equals interval 2000. Subscribe val equals. Console log interval, val, main subscription add interval sub. Add interval subscription to main. After some time, unsubscribe from the main subscription. Set timeout equals main subscription unsubscribe. This will unsubscribe both click sub and interval sub. Console log, main subscription and all children unsubscribed. 7000. This pattern is extremely useful in component-based frameworks, like Angular, where you can create a single subscription instance for a component and add all its active subscriptions to it. Then, in the component's onDestroy lifecycle hook, you simply call main subscription unsubscribe to clean up everything. Observable execution flow, a complete picture. Let's summarize the entire observable lifecycle we've covered so far. Observable definition. You define an observable, e.g., using of, from event, or new observable. At this point, nothing is happening, it's just a blueprint, cold in most cases. Observer creation. You implicitly define an observer by providing next, error, and complete handlers. Subscription. You call observable subscribe, observer. This activates the observable. The observable's internal subscribe function starts executing, and it begins pushing notifications to the provided observer. A subscription object is returned. Execution, pushing notifications, the observable pushes values via observer next. If an error occurs, observer error is called, and the stream terminates. If the stream completes successfully, observer.complete is called, and the stream terminates. Teardown. If the observable completes or errors, its internal cleanup logic, if any, is executed automatically. If the observable is long-lived, or if you no longer need the values, you explicitly call subscription unsubscribe. This triggers the observable's internal cleanup logic and stops the observer from receiving further notifications. Practical examples, bringing it to life. We've explored several small examples already. For runnable code examples that you can experiment with, definitely check the companion code repository where these concepts are shown in a practical context. This allows you to witness the next, error, and complete calls and specifically observe the effect of unsubscribe on ongoing streams like interval. Chapter summary. Taking control of the stream. You now have a firm grasp of how to listen to and manage the observable's data flow. The observer is your interface for receiving values and handling the stream's outcome, while the subscribe method activates the stream. Most importantly, the return subscription object provides the vital unsubscribe method, empowering you to manage resources, prevent memory leaks, and control the lifecycle of your reactive operations. With observables producing values and observers ready to consume them, we have the basic plumbing in place. But how do we transform these values, combine multiple streams, or filter out unwanted data? That's where the true power of RxJS begins to shine, and it's the subject of our next few chapters as we delve into the world of operators. Chapter 5. Operators Handbook Part 1. Creation and Transformation. Introduction, the power of operators. So far, we've learned that observables are streams of data, and observers subscribe to them. This is the fundamental producer-consumer relationship. But raw observables, especially infinite ones like from event or interval, often don't provide the shape or timing of data we need directly. This is where the true elegance and power of RxJS emerge, through its vast collection of operators. Operators are pure functions that take an observable as input and return a new observable as output. They allow you to transform, filter, combine, or manipulate streams in incredibly expressive and concise ways. Think of them as the building blocks or tools in a pipeline. Each operator performs a specific task, and you can chain them together to create complex data processing flows. This functional, declarative approach is what makes RxJS so potent for managing asynchronous processes. Two types of operators, conceptual. While all operators ultimately manipulate observables, it's helpful to think of them in two conceptual categories based on how you use them. Creation operators. These are standalone functions that create a new observable. We've already seen some of these in Chapter 3, e.g., of, from, interval, timer, from, event. You call them directly of 1, 2, 3. Pipeable operators. These are functions used within an observable's pipe method. They take an existing observable as input and return a new observable that has been transformed by the operator's logic. You chain them together to build a processing pipeline. Let's look at that crucial pipe method. The pipe method, building observable pipelines. The pipe method is how you chain multiple operators together in RxJS. It's a method on an observable instance and takes a variable number of operator functions as arguments. The output of one operator becomes the input of the next. Conceptual usage, full code and external repo. Import of map filter from RxJS. Const source $equals of 1, 2, 3, 4, 5. Our initial observable. Const process numbers $equals source $, pipe. Map value equals value 2, First, double each number. Filter value equals value 5. Then, keep only numbers greater than 5. To processed numbers $, subscribe value equals console log value, expected output. 6, 8, 10. Notice that processed numbers $, is a new observable. The pipe method creates a new observable that implements the specified transformations. It does not modify the original source $, observable. Source $, is still of 2, 3, 4, 5. This immutability is a key functional programming principle within RxJS. More creation operators beyond the basics. While of, from, interval, timer, and from event are common, here are a few more useful creation operators. Empty creates an observable that emits no values, then immediately completes. Useful as a placeholder or for certain conditional scenarios where you want a stream to end without emitting. Conceptual example. Empty subscribe equals console log observable completed would immediately log observable completed. Throw error equals new error, something went wrong. Creates an observable that immediately emits an error notification, then completes. Useful for scenarios where you want to produce an error stream. Note the change in RxJS 7+ requiring a factory function equals new error. Conceptual example. Throw error equals new error oops. Subscribe error equals console error would immediately log an error. Defer observable factory creates an observable that on subscription calls an observable factory function and subscribes to the observable that it returns. This operator is crucial when you want to define an observable that creates its behavior at the moment of subscription, rather than when it's defined. This can be important for ensuring that fresh state or configurations are used. Conceptual example, if you have an of date now, it captures the time when the of observable is defined. If you wrap it in defer, of date now, it captures the time when it is subscribed to. This is vital for lazy evaluation. Transformation operators, reshaping the stream's data. Transformation operators take values from a source observable, apply a function to them, and emit the result as a new value on the output observable. Map projection function applies a projection function to each value emitted by the source observable and emits the result. It's essentially the same as the map method on arrays. Use case, changing data format, performing calculations. Conceptual example. Of 1, 2, 3, pipe map value equals value 10, emits 10, 20, 30. Pluck ... properties. Extracts a nested property from each object emitted by the source observable. If the property doesn't exist, it emits undefined. Note, pluck is deprecated in favor of chaining map operators as it provides more flexibility and better type checking. Modern equivalent and conceptual example. For of, user. Name, Alice, pipemapObj equals obj.user. Name, which is preferred, emits Alice. Scan accumulator, seed, applies an accumulator function to each value emitted by the source observable and returns each intermediate result. It's similar to array.prototypeReduce, but scan emits every intermediate result, whereas reduce emits only the final one. Use case, aggregating state, building a running total. Conceptual example. Of 1, 2, 3, pipe scan, ACK val equals ACK plus val 0, emits 1, 0 plus 1, then 3, 1 plus 2, then 6, 3 plus 3. Flattening operators, higher order observables. These are some of the most powerful and often misunderstood operators. They deal with a common scenario, when an observable emits other observables, called higher order observables. You often encounter this when a stream of events triggers another asynchronous operation, like an HTTP request. You need a way to flatten these nested observables into a single, cohesive stream of values. The choice of flattening operator depends entirely on your desired concurrency and cancellation behavior. Mergemap/flatmap, concurrent, behavior, subscribes to inner observables as they arrive and merges their values onto the output stream. It processes all inner observables concurrently, and their values might interleave. Use case, when the order of inner observable results doesn't matter and you want to perform multiple asynchronous actions in parallel. Conceptual example, if a button click triggers multiple independent API calls and you want to get all their results as they come in. Analogy: multiple independent conveyor belts, inner observables, feeding items onto a main conveyor belt output stream without waiting for each other. Concat map, sequential, behavior, subscribes to inner observables one by one. It waits for the current inner observable to complete before subscribing to the next one. This guarantees the order of the inner observable's emissions. Use case: when the order of operations is critical. For instance, updating a database record must complete before fetching the newly updated data. Conceptual example: of 1, 2, 3, pipe concat map, ID equals fetch user, ID. Would fetch user 1, wait for it to complete, then fetch user 2, wait, etc. Analogy: items on a single conveyor belt are processed one after another. The next item only moves forward when the previous one is fully processed and removed. Switch map, cancellation, behavior, subscribes to an inner observable. However, if the source observable emits a new value before the current inner observable completes, switch map automatically cancels the previous inner observable's subscription and switches to the new one. Use case: the quintessential operator for type-ahead search. As the user types, you only care about the results from the latest input. Previous, slower requests should be abandoned. Conceptual example: a search input stream. When a new key is pressed, any pending API request from the previous key press is cancelled, and a new request is started for the current input. Analogy: you're watching TV. When you hit the Channel Up button, the previous channel immediately stops and the new channel begins. Exhaust map, ignore new, behavior, subscribes to an inner observable. While that inner observable is active, i.e., has not completed, exhaust map ignores all new values from the source observable. Only when the current inner observable completes will it then consider a new emission from the source. Use case: preventing multiple concurrent actions. For example, a submit button that, when clicked, disables itself until the form submission, an inner observable, completes, preventing the user from submitting the form multiple times. Conceptual example: if a user clicks a button rapidly, only the first click triggers an action, and subsequent clicks are ignored until the first action finishes. Analogy: a VIP lane at an event. Only one person at a time can go through. If someone is already in the lane, anyone else trying to enter is ignored until the current person has completely exited the lane. Choosing the right flattening operator is critical and depends entirely on the intended behavior of your asynchronous interactions. Here's a quick decision tree. Do you need to cancel previous pending operations when a new one starts? Use switch map. Do you need to ignore new operations while a current one is in progress? Use exhaust map. Do you need to process all operations, but strictly one after another, preserving order? Use concat map. Do you need to process all operations concurrently, order not important for individual results? Use merge map. Chapter summary: manipulating the data flow. In this chapter, we've begun our journey into the powerful world of RxJS operators. We've understood that operators are pure functions that allow us to transform and manipulate observables, and that the pipe method is our primary tool for chaining these operations into elegant, readable pipelines. We revisited important creation operators and then delved into the critical family of transformation operators, especially the flattening operators, merge map, concat map, switch map, exhaust map, distinguishing their unique concurrency and cancellation behaviors. With these foundational transformation tools, you can now begin to reshape the data flowing through your streams. In the next chapter, we'll continue our exploration of operators, focusing on those that allow us to filter out unwanted values and combine multiple independent streams into a single, cohesive one. Chapter 6, Operators Handbook Part 2, Filtering and Combination. Introduction: controlling the flow and merging streams. Building on our understanding of transformation operators from the previous chapter, we now turn our attention to two more powerful categories: filtering operators and combination operators. Filtering operators allow us to precisely select which values from a stream we want to keep, discarding the rest. Combination operators, on the other hand, enable us to orchestrate and merge the output of multiple independent observables into a single, unified stream. Together, these operators provide incredibly granular control over the data flowing through our reactive applications. Filtering operators: selecting what you need. Filtering operators are essential for processing only the relevant data, reducing noise, and optimizing performance by preventing unnecessary operations. Filter predicate function. Behavior emits values only if they satisfy a specified predicate function. The predicate function receives each value from the source observable and must return a Boolean true to keep, false to discard. Use case selecting specific items from a list, showing only valid inputs. Conceptual example of 1, 2, 3, 4, 5. Pipe filter value equals value percent 2 equals 0 emits 2, 4. Take count behavior emits only the first count values from the source observable and then immediately completes. Any subsequent values from the source are ignored. Use case getting the first few items, ensuring a stream stops after a certain number of emissions. Very useful for preventing memory leaks by taking only one value then completing. Conceptual example. Interval 1000, pipe take 3, emits 0 after 1s, 1 after 2s, 2 after 3s, then completes. Take while predicate function inclusive, behavior, emits values continuously as long as the predicate function returns true. As soon as the predicate function returns false for any value, take while completes the output observable and ignores all subsequent values from the source. The inclusive argument, defaults to false, determines whether the value that caused the predicate to fail is omitted. Use case reading data until a specific condition is met, e.g., red sensor data until temperature exceeds a threshold. Conceptual example of 1, 2, 3, 2, 1. Pipe take while value equals value 3, emits 1, 2, the first 3 causes completion. If inclusive is true 1, 2, 3. Take until notifier behavior. Emits values from the source observable until a notifier observable emits any value. Once the notifier emits, take until completes the output observable. Use case a very common operator for managing subscriptions and preventing memory leaks in components. You create a notifier, often a subject, that emits when a component is destroyed, and all observables active in that component pipe take until this component destroyed. Conceptual example, a long-running interval that stops when a user clicks a stop button linked to from event, stop button, click. First, predicate. Behavior emits only the first value from the source observable or the first value that satisfies an optional predicate function, and then immediately completes the output observable. Use case similar to take, 1, but with an optional condition, ensures you get exactly one value. If the source completes without emitting a value that satisfies the predicate, it will error unless a default value is also provided. Conceptual example of 10, 20, 30, pipe first val equals val 15, emits 20 then completes. Of 5, 10, pipe first val equals val 15 minus 1, emits minus 1 default value because no value satisfies prediction. Skip count behavior skips the first count values emitted by the source observable, then emits all subsequent values. Use case ignoring initial setup values, skipping header rows in data streams. Conceptual example of A, B, C, D, pipe skip 2, emits C, D. Skip while predicate function, behavior, skips values from the source observable as long as the predicate function returns true. Once the predicate function returns false for a value, skip while will emit that value and all subsequent values from the source. Use case, ignoring leading zeros or initial empty states. Conceptual example of 0, 0, 1, 2, pipe skip while value equals 0, emits 1, 2 distinct until changed compare function. Behavior only emits a value from the source observable if it is different from the last emitted value. Use case, preventing duplicate consecutive emissions, e.g., from an input field where the value hasn't actually changed, or avoiding redundant API calls. Conceptual example of 1, 1, 2, 2, 1, pipe distinct until changed, emits 1, 2, 1. Note the second one is omitted because it's different from the preceding 2. You can provide an optional compare function for complex objects. Debounce time, due time, behavior, emits a value from the source observable only after a specific due time in milliseconds has passed without any other values being emitted from the source. If a new value arrives within due time, the timer is reset. Use case, crucial for type-ahead search, prevents firing off too many API requests as a user types by waiting for a pause in their input. Conceptual example. If typing a then B then C quickly, debounce time would wait 500 ms after the C before emitting anything. If another key is pressed within that 500 ms, the timer restarts. Throttle time, duration, scheduler, config, behavior, emits the first value from the source observable, then ignores subsequent values for a specified duration. Once the duration has passed, it listens again for the next value. Use case, limiting rapid events like button clicks, window resizing, or scroll events to a manageable rate. Conceptual example, from event, button, click. Pipe, throttle time, 1000, would emit the first click, then ignore any clicks for the next 1 second. Difference from debounce. Debounce time waits for a pause in emissions. Throttle time immediately emits the first value and then enforces a cooldown period. Combination operators. Merging multiple streams. Combination operators allow you to take multiple source observables and merge, join, or concatenate their values into a single output observable. This is fundamental for reactive applications that often need to draw data from disparate sources. Merge, observables, behavior, combines multiple observables into a single output observable, interleaving values as they are emitted from any of the source observables. The order of emissions within each source observable is preserved, but the order between different sources is determined by whichever emits first. Use case, consolidating events from multiple input sources, e.g., clicks on 2 different buttons, showing data from 2 independent API calls as they arrive. Conceptual example, merge of A, B, of 1, 2, could emit A, 1, B, 2, or 1, A, 2, B, etc. depending on timing. Completion happens when all source observables complete. Concat, observables, behavior, combines observables sequentially. The next observable only subscribes and begins emitting after the previous observable has completed. This guarantees strict order. Use case, executing asynchronous operations in a specific sequence, ensuring that one task finishes before the next begins. Conceptual example, concat of hello, interval 1000, pipe take 3, would first emit hello immediately, then emit 0, 1, 2 from the interval after 1, 2, 3 seconds respectively. Completion happens when the last source observable completes. Combine latest, observables, project, behavior, emits a value when any of the input observables emits, combining the latest values from all inputs. All input observables must have emitted at least one value before the combine latest starts emitting. Use case, when you need the most up-to-date values from several independent sources, e.g., form validation, where an enabled button depends on the latest input from multiple fields. Conceptual example, if obs.A emits A1, A2 and obs.B emits B1, B2 combine latest, obs.A, obs.B would emit A1, B1, after both have emitted, then A2, B1. When A2 comes in, then A2, B2, when B2 comes in. Fork join, observables. Behavior, takes an array or object of observables and emits a single value, an array or object, when all input observables complete, containing the last value from each. If any input observable errors, fork join will error. If any input observable never completes, fork join will never emit. Use case, similar to promise all. Useful for making multiple independent HTTP requests and waiting for all of them to finish before proceeding. Conceptual example, fork join of 1 of hello, emits 1, hello only after both have completed. Zip, observables project, behavior, combines values from observables in pairs based on their index. It waits for one value from each observable to arrive before emitting a new array containing those values. If one observable emits more values than another, the extra values are buffered until a corresponding value from the other observables arrives. The output observable completes when any input observable completes. Use case, combining events that semantically belong together, e.g., getting a response from multiple servers for the same query, effectively pairing request and response from different sources. Conceptual example, zip of A, B, of 1, 2, 3, emits A, 1, then B, 2. It will not emit 3 because one observable completed before the third pair, with latest from Observables project behavior. Combines the latest value from the source observable with the latest values from other observables only when the source observable emits. The values from the other observables are essentially sampled when the source emits. Use case. A common pattern is to combine a user action, e.g., a button click, with the current state of an application, e.g., form data, user ID. Conceptual example. Clicks $pipe with latest from document get element by ID my input. Value would emit click event, input value, whenever a click occurs, with input value being the current value of the input field at the time of the click. Decision guide, when to use which combination operator. Parallel execution, all results complete together. Fork join. Parallel execution, results interleave as they arrive. Merge. Sequential execution, one after another. Concat, need latest value from multiple independent sources, updated whenever any source changes. Combine latest. Need latest value from other sources, only when the primary source emits. With latest from, need to pair values by index from multiple sources. Zip. Chapter summary, precision and harmony in streams. We've significantly expanded our RxJS toolkit in this chapter. The filtering operators provide the precision needed to prune our streams, allowing us to select only the most relevant data and manage event rates effectively with debounce time and throttle time. The combination operators, on the other hand, are the orchestrators, enabling us to elegantly merge, sequence, or join data from multiple independent observables. You now possess a powerful array of tools to manage and shape your asynchronous data flows. In the next chapter, we'll round out our operator discussions by exploring utility operators for side effects and debugging, and, critically, robust strategies for error handling in our reactive applications. Chapter 7, Operators Handbook Part 3, Utility and Error Handling. Introduction, Stream Utilities and Resilience. In our journey through the RxJS operator landscape, we've covered how to create, transform, filter, and combine observables. These are the workhorses of data manipulation. However, a robust application needs more. It needs ways to perform side effects cleanly, like logging for debugging, manage timing beyond simple debouncing, and, perhaps most critically, handle errors gracefully. This chapter focuses on utility operators, which aid in stream management and debugging, and provides a deep dive into error handling strategies, a crucial aspect of building resilient reactive applications. Utility operators. Enhancing and inspecting streams. Utility operators don't typically change the values of a stream, but rather provide ways to interact with the stream's lifecycle or for debugging purposes. Tap, observer or next, error complete. Behavior allows you to perform side effects for notifications from the source observable without modifying the stream itself. It taps into the stream. Use case. Debugging, logging values, errors, or completion at various points in a pipeline, adding analytics, or performing non-blocking side effects, like updating UI elements that don't depend on the stream's values. Conceptual example. /conceptual usage, full code in external repo. Import of map tap from RxJS, of 1, 2, 3, pipe. Tap value equals console log before map, value. Map value equals value 2. Tap, next, value equals console log after map, value. Complete equals console log stream done with tap. Subscribe, expected output before map, 1. After map, 2. Before map, 2. After map, 4. Before map, 3. After map, 6. Stream done with tap. Note, tap replaced the older do operator, offering a more flexible interface where you can provide an object with next, error, and complete methods, similar to how subscribe works. Delay, do time, behavior, delays the emission of values from the source observable by a specified do time in milliseconds. It also delays the error and complete notifications. Use case. Simulating network latency, introducing pauses in animations, or synchronizing events. Conceptual example of hello, pipe delay 2000 would emit hello only after 2 seconds. Delay when delay duration selector, behavior. delays emissions using a delay duration selector function, which receives the source value and returns an observable. The source value is delayed until that duration observable emits its first value or completes. Use case: more complex, dynamic delays, like delaying subsequent API calls until the previous one completes, not just emits values. Note: less commonly used than delay for simple time-based delays. Timeout due time scheduler, /timeout with due time with observable scheduler. Behavior: emits a timeout error if the source observable doesn't emit any value within due time milliseconds, or if it doesn't emit the first value within due time. Timeout with allows you to switch to another provided with observable stream when the timeout occurs, instead of just throwing an error. Use case: preventing hanging operations, e.g., if an API call takes too long, displaying user-friendly messages for slow responses. Conceptual example: interval 1000, pipe timeout 500 would error because values are emitted every 1000 ms, but timeout is set at 500 ms. Finalize callback behavior: schedules a callback function to run when the source observable completes or errors, regardless of how it terminates. Use case: performing cleanup operations, e.g., hiding a loading spinner, logging final status, similar to a finally block in try.catch. Conceptual example of 1, pipe finalize equals console log cleanup, subscribe would log cleanup. After emitting 1 and completing. Error handling in reactive streams. Strategies for resilience. One of the most powerful and often challenging aspects of asynchronous programming is error management. In RxJS, understanding how errors propagate and how to handle them is paramount for building robust applications. The observable is terminated on error principle. This is the most critical rule in RxJS error handling. When an observable sequence emits an error notification, the sequence terminates. It will not emit any further next or complete notifications. The observable instance is effectively dead. This behavior might seem harsh at first, but it ensures predictability and prevents unexpected behavior from corrupted or half-finished streams. It forces you to explicitly decide how to recover or react when an error occurs. Consider an observable that makes an HTTP request. If that request fails, the observable associated with it errors and terminates. Any subsequent emissions from that specific observable instance are impossible. If you want to retry the request or switch to fallback, you must do so by creating or switching to a new observable. Here are the primary error handling operators. Catch error selector. Behavior: intercepts an error notification from the source observable. The selector function receives the error and the source observable. Inside this function, you can either return a new observable. This replaces the failed stream with a new, potentially different observable. The original stream is terminated, but the main pipeline continues with the new stream. Rethrow the error. If you rethrow the error, it means you've handled something but still want the error to propagate down the chain, effectively terminating the rest of the pipeline at that point. Use case: providing fallback data, displaying user-friendly error messages, logging errors to analytics, gracefully degrading functionality. This is the most common and versatile error handling operator. Conceptual example: replacing the stream on error. /conceptual usage, full code in external repo. Import of throw error from RxJS. Import catch error from RxJS/operators. Const API call $= throw error equals new error API failed. API call $pipe. Catch error. Console error caught error providing fallback, error message, return of fallback data. Replace the error stream with a new observable. Subscribe. Next, val equals console log received, val. Error equals console, error this should not happen, this won't be called. Complete equals console log, stream completed. Expected output, caught error providing fallback, API failed, received, fallback data. Stream completed, conceptual example. Rethrowing a processed error. API call $pipe. Catch error. Console error logging error, then rethrowing, error message, can also return throw error, equals new error, for new error. Throw error. Rethrow the original error. Subscribe. Next, val equals console log received, val. Error equals console error, final error handler, or message, this will be called. Complete equals console log, this will not happen. Is expected output, logging error then rethrowing, API failed. Final error handler, API failed, retry count, behavior. If the source observable emits an error, retry will resubscribe to the source observable a specified number of count times. If count is omitted or negative, it will retry indefinitely. Once the retries are exhausted and an error still occurs, the error is propagated down the chain. Use case: handling transient network failures or temporary server unavailability. Conceptual example: /conceptual usage, full code in external repo. Import timer, throw error from RxJS. Import merge map, retry from RxJS/operators. Let attempt equals 0. Const flaky API $timer, pipe. Merge map equals attempt ++ if attempt 3. Console log attempting API call flaky, return throw error, equals new error temporary failure. Else, console log API call succeeded, return of success. Flaky API $pipe. Retry 2, retry up to 2 times, total 3 attempts. Subscribe. Next, val equals console log received, val. Error equals console error, final error, message. Expected output, attempting API call flaky. Attempting API call flaky. API call succeeded. Received, success. Retry when, notifier factory. Behavior, provides a more sophisticated and customizable retry mechanism. It takes a factory function that receives an observable of errors. The job of the notifier factory is to return another observable. If this notifier observable emits a value, the source observable is retried. If the notifier observable completes or errors, then the original error is propagated. Use case: implementing exponential backoff, retrying with increasing delays, retrying only for specific error codes, or retrying only a certain number of times before giving up. Conceptual example: retrying with increasing delays, exponential backoff. This requires a more complex pipe within retry-when, but allows fine-grained control. Importance of operator placement in the pipe when dealing with errors. The position of catch error matters significantly. Catch error only catches errors from the observable upstream of it in the pipe. /conceptual usage, full code in external repo. Import of map catch error from RxJS. Scenario 1, error before catch error. Of 1-2, error for pipe. Map val equals, if typeof val equals number. Throw new error, not a number. Return val 2. Catch error equals. Console error caught in pipe, message, return of 0. Recovery. Subscribe. Next, val equals console log result, val. Error equals console error sub error, message. Expected. Caught in pipe, not a number. Result, 0. Scenario 2. Error after catch error. This will terminate the subscription directly. Of 1-2-3, pipe. Catch error equals of 0. This catch error won't see the error defined below. Map val equals. If val equals 2. Throw new error, specific value error. This error is omitted after catch error. Return val 2. Subscribe. Next, val equals console log result, val. Error equals console error sub error, message, this will be called. Expected, sub error. Specific value error. Place catch error strategically where you anticipate errors and where you want to recover. If you want to handle any error that propagates down the entire pipeline, place a catch error operator as the last operator in your pipe, or handle it directly in the subscribe error handler. Common error handling patterns. Displaying user-friendly messages. Use catch error to intercept an API error, then return an observable emitting a user-facing message or a flag to show an error banner. Logging errors. Use tap to log the error to a monitoring service before rethrowing it with catch error or handling it. Graceful degradation. On a specific service error, use catch error to return an empty observable or an observable with default data, allowing the rest of your application to function. Loading states. Combine catch error with finalize or tap to ensure loading spinners are always hidden, regardless of success or failure. Chapter summary. robust and debuggable streams. This chapter has provided you with essential tools for building resilient and inspectable reactive applications. We've explored utility operators like tap for debugging and side effects, delay for timing, and finalize for guaranteed cleanup. Most importantly, we delved into the fundamentals of RxJS error handling, understanding the crucial termination on error principle and how to recover or react using catch error and retry, or the more advanced retry when. The strategic placement of catch error in your operator pipeline is key to effective error management. With these skills, you're well equipped to create more stable and maintainable reactive systems. In the next chapter, we'll move beyond single-point subscriptions to explore subjects, a specialized type of observable that offers powerful multicasting capabilities and is often used for state management and intercomponent communication. Chapter 8, Subjects, Multicasting and State Management. Introduction, Sharing Observable Executions. Up until now, when we've subscribed to an observable, each subscription has triggered a new, independent execution of that observable. This is the nature of cold observables, which, as we discussed in Chapter 3, emit their sequence of values only when and for each time an observer subscribes. Think of a video file on demand. Each viewer gets their own stream, starting from the beginning. However, many real-world scenarios require a different behavior. Imagine a live sports broadcast, a chat application, or a global application state. In these cases, you don't want each new listener to start a new show or trigger a fresh data fetch. Instead, you want all listeners to receive the same stream of events or the current state. This concept is called multicasting, broadcasting a single stream to multiple observers. This is where subjects come into play. Subjects are a special type of observable that are inherently hot and enable multicasting. What is a subject? A subject is a unique type in RxJS because it acts as both an observable and an observer. As an observer, it can next, error, and complete values, meaning you can manually push values into a subject. As an observable, it can be subscribed to by multiple observers, and when a value is pushed into the subject, all its current subscribers receive that value simultaneously. This dual nature makes subjects perfect for bridging non-reactive codebases with reactive ones, implementing event buses, or managing shared state within an application. Think of a subject like a public address system or a radio station. Anyone can speak into the microphone calling next, error, or complete on the subject, and anyone tuned into the station, subscribing to the subject, hears the broadcast. Regardless of when a person tunes in, they hear what's being broadcast from that moment forward. /conceptual usage, full code in external repo. Import subject from RxJS. Const mySubject equals new subject string. Observer1 subscribes. MySubject subscribe value equals console log observer1 value MySubject next hello. Emits to observer1. Observer2 subscribes later. MySubject subscribe value equals console log observer2 value MySubject next world. Emits to observer1 and observer2. MySubject.complete signals completion to both observers. MySubject next. This will not be emitted as subject completed. Expected output. Observer1 hello. Observer1 world. Observer2 world. Notice that observer2 did not receive hello because it subscribed after hello was emitted. This is the default behavior of a basic subject. Types of subjects. RxJS provides several specialized types of subjects, each with slightly different behaviors regarding how they handle values for new subscribers. Subject, basic subject. Behavior, the most fundamental subject. It multicasts values to all its current subscribers at the moment values are emitted. It does not have an initial value and does not retain a history of past emissions for new subscribers. Use case. Simple event bus, converting a hot source, like DOM events, into an observable sequence that can be pushed to. Behavior subject. Behavior, a subject that holds a current value. It requires an initial value when created. When a new observer subscribes, it immediately receives the behavior subject's current value, the last emitted value, or the initial value. After that, it behaves like a regular subject, emitting all subsequent values to its subscribers. Use case, representing and managing, state that components need immediate access to upon subscription. Common in state management, patterns e.g. in ng-rx or simple state services. Conceptual example. Import behavior subject from RxJS. Const myBSubject equals new behavior subject number 0. Initial value is 0. MyBSubject subscribe, value equals console log obs1, value. Obs1 gets 0. MyBSubject next 1, obs1 gets 1. MyBSubject next 2, obs1 gets 2. MyBSubject subscribe, value equals console log obs2, value. Obs2 gets 2, the current value. MyBSubject next 3, obs1 gets 3, obs2 gets 3. Expected output, obs1, 0. Obs1, 1. Obs1, 2. Obs2, 2. Obs1, 3. Obs2, 3. Replay subject, buffer size, window time. Behavior. Stores a buffer of previous values emitted by the subject and re-emits them to new subscribers immediately upon subscription. You can configure buffer size, the maximum number of past values to replay. Window time, the maximum time in milliseconds a value can stay in the buffer. Use case, providing a history of recent events to new subscribers, useful for audit logs, or when new components need to catch up on recent activity. Conceptual example. Import replay subject from RxJS, const myRSubject equals new replay subject string 2, buffer size of 2. MyRSubject next A, MyRSubject next B. MyRSubject next C, A is dropped from buffer. MyRSubject subscribe, value equals console log obs1, value, gets B, C. MyRSubject next to D. Obs1 gets D. MyRSubject subscribe, value equals console log obs2, value, gets C, D. Observed output varies depending on timing, but ensures latest 2 values are replayed. Async subject, behavior. This subject is unique because it only emits the last value produced by the source observable, and it only emits it when the source observable completes. If the source observable errors, async subject will not emit anything and simply propagate the error. Use case, when you are interested only in the final result of an asynchronous operation that might take time. Conceptual example. Import async subject from RxJS, const myASubject equals new async subject string. MyASubject next, value 1, MyASubject next, value 2. This is the last value before completion. MyASubject subscribe, value equals console log obs1, value, myASubject.complete. Now value 2 is emitted to obs1. MyASubject subscribe, value equals console log obs2. Value, obs2 also gets value 2. Expected output, obs1, value 2. Obs2, value 2. Multicasting operators. Beyond manual subjects. While you can directly use subjects to achieve multicasting by manually calling subject next. RxJS provides operators that make it easier to make a cold observable hot and share its execution among multiple subscribers. These operators internally use subjects. Share, behavior, returns a multicasted observable that remains subscribed to the source as long as there is at least one subscriber. When the last subscriber unsubscribes, the connection to the source is automatically torn down. When a new subscriber then comes along, it will resubscribe to the source. It does not replay any past values. Use case. Making a cold, e.g., HTTP request, observable hot so that multiple subscribers share the same network call, but preventing the call from running if no one is listening. Conceptual example. If an API call is wrapped in source $pipe share, the API call will only be made once when the first observer subscribes. If all observers unsubscribe, the connection is closed. If a new observer subscribes after that, the API call is made again. Share replay, buffer size, window time, scheduler, behavior. This is one of the most commonly used multicasting operators. It multicasts the source observable's execution and also replays a specified number of past values to new subscribers. It intelligently manages its connection to the source. It connects when the first subscriber arrives and disconnects when the last subscriber unsubscribes, unless ref count logic and buffer size are configured differently. Use case. Caching the results of an expensive operation, like an HTTP request. so that subsequent subscribers receive the cached result instantly without re-executing the source. Often preferred over share, when new subscribers still need the latest emitted value. Conceptual example, HTTP get $users. Pipe share replay 1 will make the HTTP request once. All subsequent subscribers will immediately get the result of that single request. When a subscriber connects, it immediately receives the last value, the one in share replay 1. When to use share replay versus directly using a behavior subject. While share replay internally uses a replay subject and behavior subject is a type of subject, they serve slightly different purposes. Behavior subject, used when you are responsible for actively next-ing values into it to manage a piece of state. It's often used within a service that encapsulates application state. You control when values are pushed. Share replay, used when you have an existing observable, e.g., from an API call that already pushes values, and you want to share and cache its results for multiple passive subscribers. You are making an existing cold observable hot and replaying its past values. It's less about active state management and more about resource optimization and caching. Basic state management with behavior subject. Behavior subject is particularly well suited for simple application state management, often seen in services or stores. Because it always holds a current value and immediately emits it to new subscribers, it behaves like a reactive getter. For example, a simple counter service. /conceptual usage, full code in external repo. Import behavior subject, observable from RxJS. Class counter service, private count, behavior subject number equals new behavior subject, 0. Expose count as an observable, preventing external pushing via next. Public read-only count. Observable number equals this dot count as observable. Increment. This dot count next, this dot count value plus 1. Decrements. This dot count next, this dot count value 1. Const counter equals new counter service. Counter dot count dollar. Subscribe val equals console log, current count, val, immediately gets 0. Counter dot increment, gets 1. Counter dot increment, gets 2. Another part of the app subscribes. Counter dot count dollar. Subscribe val equals console log another subscriber, val, immediately gets 2. Counter dot decrement, both subscribers get 1. Expected output sequence that demonstrates state handling. This pattern provides a clear, reactive way to manage and interact with a piece of shared state, ensuring that any component interested in the count always receives its latest value. Chapter summary, shared streams and core state. Subjects are powerful tools for introducing multicasting into your reactive applications, allowing a single observable execution to be shared by multiple observers. We've explored the core subject and its specialized variants, behavior subject, replay subject, async subject, understanding their unique behaviors regarding initial values and value re-emission. We also introduced the important share and share replay operators, which streamline the process of making cold observables hot and caching their results. Finally, we demonstrated how behavior subject can be effectively used for simple, reactive state management. With the ability to multicast, your reactive applications become more efficient and capable of handling shared data and events globally. In the next chapter, we'll delve into schedulers, a more advanced topic that gives you fine-grained control over the execution context and timing of your observables, crucial for optimizing performance in complex asynchronous workflows. Chapter 9, Concurrency and Schedulers, Managing Execution Context. Introduction, Time and Place in Reactive Programming. So far, we've focused on what values observables produce and how they're transformed and combined. But in JavaScript, especially in a browser environment, when and where a piece of code runs can be just as crucial. Tasks can be immediate, deferred, run after a short delay, or even synchronized with the browser's repaint cycle for smooth animations. This is where schedulers come into play. Schedulers in RxJS are a relatively advanced topic, and for many common RxJS use cases, you won't need to interact with them directly. RxJS operators have sensible default schedulers built in. However, understanding schedulers provides a deeper insight into how RxJS manages concurrency, controls execution timing, and operates within JavaScript's asynchronous event loop. It's often when optimizing performance, synchronizing complex UI operations, or debugging subtle timing issues that you'll leverage schedulers explicitly. What is a scheduler? A scheduler in RxJS is an abstraction that controls two things when a task is executed. This refers to the timing strategy, whether it's immediate, asynchronous, or delayed. Where a task is executed, this refers to the execution context. Is it on the current event loop turn, in a micro task, or a macro task? You can think of a scheduler as a dispatcher or a specialized queue for tasks. When an observable needs to perform an asynchronous operation, like emitting a value after a delay or subscribing to itself, it delegates that task to a scheduler. RxJS's built-in schedulers. RxJS provides several built-in schedulers, each with a specific execution strategy. Async scheduler, behavior, schedules tasks asynchronously using set timeout or set interval for recurring tasks. This means the task will be put at the end of the browser's macrotask queue. Use case, default for time-based operators like interval, debounce time, throttle time, delay. For most common asynchronous operations that don't need immediate or micro-task execution. Conceptual example, interval, 0, async scheduler will still defer to the next tick despite having a 0 ms delay. ASAP scheduler, behavior, schedules tasks on the micro-task queue, which is executed as soon as the current script finishes, but before the browser's repaint and before tasks in the macrotask queue, like set timeout. This is the same queue used by promises, as soon as possible. Use case, for tasks that need to be asynchronous but should run with higher priority than set timeout, and are suitable for the micro-task queue, e.g., small computations, promise resolutions. Conceptual example, if you need to perform an operation asynchronously, but you want it to happen before any browser repaint or long-running set timeout tasks. Queue scheduler, behavior, schedules tasks synchronously or by queuing them up to run one after another immediately. If a task is scheduled on queue scheduler, it will be executed without delay, after the currently executing synchronous code, but before other types of asynchronous tasks. Use case ensures strict sequential execution for a series of tasks. It's often used internally for operators that guarantee synchronous processing of an observable sequence, ensuring that no intertask delays occur. Conceptual example, range 1-5 queue scheduler would emit values 1 to 5 synchronously within the current call stack, not deferring them. Animation frame scheduler, behavior, schedules tasks using request animation frame. This means the task will run just before the browser performs its next repaint. Use case, for highly performant DOM manipulations and animations, as it synchronizes with the browser's rendering cycle, preventing visual jank. Conceptual example, interval 0 animation frame scheduler pushes values to synchronize with animation frames. The default scheduler behavior. Many RxJS operators, if not given an explicit scheduler, will use a default that makes sense for their operation. For example, interval uses async scheduler by default because it's a time-based operation. Of and from, for arrays, typically emit synchronously in the current context unless told otherwise. The key takeaway is that when you create an observable or use cert operators, they internally decide which scheduler to use to deliver their notifications. Controlling execution. Observe on and subscribe on. While a scheduler determines when an operation happens, observe on and subscribe on let you explicitly control the execution context of different parts of your observable chain. Observe on scheduler. Behavior. This operator affects where the observable's notifications, next, error, complete, are delivered to the observer after this operator in the pipeline. It changes the execution context for all subsequent operators downstream and for the observer's handlers, subscribes callbacks. Placement, placed within the pipe, method. / conceptual usage, full code in external repo. Import of observe on async scheduler from RxJS. Console log start sync. Of 1, 2, 3, pipe. Values 1, 2, 3 are created synchronously, but their emission to the subscriber, and any operators after observe on will be async. Observe on async scheduler. Subscribe value equals console log received. Value, console log end sync. Expected approximate output, start sync. End sync. Received 1 after a short delay. Received 2 after a short delay. Received 3 after a short delay. In this example of 123 completes synchronously, but observe on async scheduler intercepts these values and puts them onto the set timeout queue. So the subscribe handler runs asynchronously. Subscribe on scheduler behavior. This operator affects where the subscription logic, the observables creation function, is executed. It dictates the context in which the observable starts and performs its initial setup. It essentially moves the point where the actual work of the source observable begins to the specified scheduler. Placement. Generally placed at the very end of the pipe method, but its effect is applied upstream to the source observable. Only the first subscribe on in a chain has an effect. /conceptual usage, full code in external repo. Import observable subscribe on async scheduler from RxJS. Const myasync observable equals new observable subscriber equals console log observable creation logic executed. Subscriber next data subscriber.complete console log before subscribe myasync observable pipe. This makes the observables creation logic itself run asynchronously. Subscribe on async scheduler. Subscribe value equals console log received. Value console log after subscribe. Expected approximate output before subscribe. After subscribe. Observable creation logic executed. After a short delay. Received data. Here, the observable creation logic executed will appear after subscribe, demonstrating that subscribe on deferred the observables setup to the async scheduler. The key difference. Observe on affects the schedule of notifications, while subscribe on affects the schedule of the subscription itself, the initial execution of the observable. Practical use cases for schedulers. While often implicit, schedulers are vital for UI updates. In browser environments, if you're performing heavy computations within an observable chain and then updating the DOM, you might want to ensure the final DOM update occurs within the animation frame scheduler to prevent jank. For most simple updates, standard async operations on the main thread are fine. Preventing UI freezes. If you have an observable doing a CPU-intensive synchronous task and you want to prevent it from blocking the main thread, you can use subscribe on async scheduler to push the task off the immediate call stack. Testing time-dependent code. As we'll see in Chapter 11, Test Scheduler is a type of scheduler that allows you to simulate the passage of time synchronously, making unit testing of time-based observables much easier and more deterministic. Cross-environment consistency. Schedulers abstract away the underlying platform's concurrency mechanisms, e.g., set timeout in browsers, process next tick in Node.js, allowing your RxJS code to behave consistently across different JavaScript environments. It's important to note that schedulers do not introduce true multi-threading in JavaScript, which is single-threaded. They leverage the event loop to manage when functions execute, giving the illusion of concurrency. Web workers can provide actual multi-threading, and RxJS can certainly be used within web workers. Chapter summary: orchestrating RxJS operations. Schedulers are the unsung heroes of RxJS, quietly managing the when and where of your observable operations. We've explored the primary built-in schedulers, async, ASAP, queue, animation frame, and their distinct execution models. Crucially, we distinguished between observe on, which controls where notifications are delivered, and subscribe on, which controls where the observable subscription logic is executed. While you may not use schedulers every day, understanding their role empowers you to fine-tune the performance of your reactive applications, debug subtle timing issues, and truly master the asynchronous nature of JavaScript. With our fundamental building blocks now firmly in place, the next chapter will bring everything together, demonstrating how to apply these concepts to solve real-world development problems. Chapter 10. Bringing it all together. Real-world RxJS patterns. Introduction: from concepts to applications. We've now methodically built up a comprehensive understanding of RxJS. From observables and observers to a wide array of operators for creation, transformation, filtering, combination, and error handling, and finally, the nuances of subjects and schedulers. you have a powerful toolkit at your disposal. The challenge now is to bridge the gap between theoretical knowledge and practical application. This chapter is dedicated to demonstrating how to apply these concepts to common, real-world problems in client-side web development. Each case study will illustrate patterns for composing multiple operators to achieve a desired behavior, highlighting the elegance and expressiveness RxJS brings to complex asynchronous workflows. While the examples focus on web development, the underlying reactive principles are transferable to many JavaScript environments. Remember, the full, executable code for these examples will be available in the accompanying online repository. This allows you to run, modify, and experiment with the solutions firsthand. Case Study 1, Autocomplete Search Box, Type Ahead Search. This is a classic problem that perfectly showcases RxJS's strengths, particularly the debounce time and switch map operators. Requirement: create a search input field. As the user types, make an API call to fetch suggestions. Debounce: don't make an API call on every keystroke, wait for a brief pause in typing. Distinct: only make an API call if the search term has actually changed since the last fetch. Cancel old requests. If the user types a new character while a previous search request is still in flight, cancel the old request and start a new one, as only the latest search matters. RxJS pattern. From event right arrow pipe right arrow map right arrow debounce time right arrow distinct until changed right arrow switch map right arrow catch error. / conceptual pattern, full code in external repo. Import from event of empty from RxJS. Import debounce time distinct until changed map switch map catch error from RxJS / operators. Assume this is our mock API call. Const mock search API equals term. String equals console log making API call for term, simulate network delay. Return new observable, observer equals const delay equals math random, 1000 plus 300. Random delay between 300 ms and 1300 ms. Const timeouted equals set timeout equals if term dot includes error, observer error, new error, simulated API error. Else, observer next, result for term 1, result for term 2, observer dot complete. Delay, teardown logic for cancellation. Return equals console log API call for term, cancelled. Clear timeout, timeout ID. Const search input equals document get element by ID search input as HTML input element. Const search dollar equals from event, search input, pipe. Map event equals event target as HTML input element, value, get the input value. Debounce time, 300. Wait for 300 ms pause in typing. Distinct until changed. Only proceed if value actually changed. Switch map search term equals cancel previous outstanding requests. If search term length 2. Return of, don't search for very short terms, return empty array. Return mock search API search term, pipe. Catch error, console error, search API error, error message, return empty. Return an observable that immediately completes if error. Catch error, catch errors from upstream operators, e.g. map. Console error, stream error, outside API call, error message, return empty. Search dollar subscribe, results equals console log search results, update UI with results. This pattern is incredibly efficient. Debounce time reduces API calls. Distinct until changed prevents redundant calls if the user types and then deletes the same character. Switch map ensures that only the latest search request results are considered, automatically canceling older, slower ones. Catch error, empty, gracefully handles API failures without breaking the mainstream. Case Study 2, implementing drag and drop. This example beautifully demonstrates how a series of related DOM events can be composed into a single, logical flow. Requirement: enable a user to drag an element across the screen. RxJS pattern. From event, for mouse down, mouse move, mouse up, right arrow pipe right arrow switch map right arrow take until right arrow map. / conceptual pattern, full code in external repo. Import from event, from RxJS. Import switch map take until map tap from RxJS / operators. Const draggable equals document get element by ID, draggable as HTML element. const mouse down dollar equals from event, draggable, mouse down, const mouse move dollar equals from event, document, mouse move, const mouse up dollar equals from event, document, mouse up, mouse down dollar pipe, tap event equals, prevent default drag behavior to avoid ghosting, event prevent default, draggable as HTML element, style position equals absolute, ensure draggable positionable, switch map start event equals, const start x equals start event as mouse event, client x, const start y equals start event as mouse event, client y, const initial left equals draggable offset left, const initial top equals draggable offset top, return mouse move dollar, pipe, map move event equals, const move x equals move event as mouse event, client x, const move y equals move event as mouse event, client y, return, left, initial left plus move x start x, top, initial top plus move y start y, take until mouse up dollar, stop dragging when mouse button is released, subscribe position equals, draggable style left equals position left px, draggable style top equals position top px. Here, mouse down dollar acts as the trigger. Switch map creates an inner observable, mouse move dollar, that only emits while the mouse is down. Take until mouse up dollar ensures that the mouse move dollar stream for a specific drag session completes cleanly when the mouse button is released. The map operator calculates the new position, and tap prevents browser default dragging behaviors. Case Study 3. Chaining dependent API calls. Often, you need to make an API call, and then use data from its response to make another API call. Requirement: fetch user details by ID. Once user details are received, fetch that user's posts. Once posts are received, filter them and fetch comments for each of the filtered posts, showing a loading indicator. RxJS pattern: HTTP call, right arrow pipe right arrow merge map, or concat map, right arrow filter right arrow fork join right arrow map right arrow lifecycle, loading error. / conceptual pattern, full code in external repo. Import of fork join observable behavior subject empty from RxJS. Import merge map, catch error, filter, tap, finalize from RxJS / operators. Mock API functions for illustration. Const mock fetch user by id equals userid. String equals console log fetching user, userid, return of id, userid name, userid posts, post 1, post 2, post 3, pipe. Simulate network delay. Delay 500. Const mock fetch post details equals posted, string equals console log fetching post details, posted, return of id, posted title, title for posted, pipe. Delay 300. Const mock fetch post comments equals posted, string equals console log fetching comments for post, posted, if posted equals post 2, return throw error, equals new error, simulated comment error for post 2, return of comment A for posted, comment B for post IDs, pipe. Delay 400. Const userid equals U123. Const loading dollar equals new behavior subject false. Loading dollar subscribe is loading equals console log loading is loading. Orchestrating dependent calls of user ID, pipe. Tap equals loading dollar next true, start loading. Merge map uid equals mock fetch user by ID uid, fetch user. Merge map user equals filter posts, then fetch comments for each. Const filtered posteds equals user posts filter, p equals p dot includes post 3. Example filter. Const comment observables equals filtered post IDs map, post ID equals mock fetch post comments, post ID, pipe. Catch error equals console error, error fetching comments for posted, message. Return of, return empty array for failed comment fetch. Return fork join, comment observables, pipe. Wait for all comment fetches to complete. Map comments equals user comments, combine user and comments. Catch error equals console error, error within fork join should not happen with inner catch error. Message. Return empty. Propagate the error if it somehow escapes inner catch error. Finalize equals loading dollar next false. Stop loading when stream completes or errors. Catch error equals catch any errors that propagated up. Console error top level error handler. Message. Return empty. Subscribe. Next, data equals console log, user and comments, data. Complete equals console log, all data fetched. This complex chain uses merge map for sequential fetching, user then posts. Inside the merge map for posts, we filter posts and then use fork join to make parallel comment fetches for selected posts. Catch error is used strategically at different levels. Inside, mock fetch post comments to handle individual post comment failures, allowing others to succeed, and at the top level for any unhandled errors. Behavior subject and tap finalize manage the loading state. Case study 4, real-time form validation. Managing validation across multiple form fields requires combining their latest values. Requirement: a login form with username and password fields. The submit button should only be enabled if both fields meet minimum length requirements. RxJS pattern. From event, for each input, right arrow pipe right arrow map right arrow combine latest right arrow map right arrow subscribe. / conceptual pattern, full code in external reap. Import from event, combine latest from RxJS. Import map, start with, from RxJS / operators. Const username input equals document get element by ID, username, as HTML input element. Const password input equals document get element by ID, password, as HTML input element. Const submit button equals document get element by ID, submit button, as HTML button element. Create observables for each input's value. Const username $ equals from event, username input, key up, pipe. Map event equals, event target as HTML input element, value. Start with username input value, to get initial value on subscription. Const password $ equals from event, password input, key up, pipe. Map event equals, event target as HTML input element, value. Start with password input value, to get initial value on subscription. Combine the latest values from both inputs. Const form validity $ equals combine latest, username $, password $, pipe. Map, username, password, equals username length equals 3 and password length equals 6. Subscribe to update the button's disabled state. Form validity $, subscribe, is valid equals. Submit button disabled equals is valid, console log form valid, is valid. Initially, form will be invalid. As user types, button will enable disable dynamically. Start with is crucial here to ensure combine latest emits an initial value when subscribed, reflecting the form's initial state. Combine latest then efficiently updates the button status whenever either input changes. Case study 5, building a simple countdown timer. Requirement: display a countdown from 10 seconds to 0, updating every second. RxJS pattern, timer or interval right arrow pipe right arrow map take. / conceptual pattern, full code in external reap. Import timer from RxJS. Import map take tap from RxJS / operators. Const display equals document get element by ID countdown display as HTML element. Const initial count equals 10. Timer 0 1000. Pipe start immediately, tick every 1 second. Map count equals initial count, transform 12 to 1098. Take initial count plus 1, take 11 values 0 to 10. Tap val equals console log countdown, val log for demonstration. Subscribe. Next, val equals display text content equals val to string. Complete equals display text content equals time up, console log countdown complete. This concise example uses timer to create a ticking stream, map to transform its values into a countdown, and take to ensure it stops exactly at 0. General reactive patterns and tips, managing loading states. As shown in case study 3, behavior subject is excellent for managing global loading states. Tap equals loading next, true, before a potentially long-running operation, and finalize equals loading next, false, to reset the state regardless of success or error. Error handling for UI. Use catch error to display user-friendly messages for API failures. You can return an empty observable or an observable of default data of within catch error to prevent the mainstream from breaking and allow the application to continue functioning. Async pipe in Angular. While not an RxJS operator, framework features like Angular's async pipe are built to consume observables directly, handling subscription and unsubscription automatically, making it a very clean way to use RxJS in templates. Similar patterns exist in other frameworks. Chapter Summary, Practical Mastery. This chapter has moved beyond the individual operators and illustrated how they combine to form elegant, powerful solutions for common challenges in web development. By seeing how debounce-time and switchmap create a robust search, how event streams are orchestrated for drag and drop, how mergemap and fork-join handle dependent API calls, how combine latest drives real-time form validation, and how timer and take build a countdown, you should now feel confident in identifying and applying RxJS patterns to your own projects. With these practical examples, you're well on your way to becoming proficient in reactive programming. In the next chapter, we'll address another critical aspect of building robust applications: testing reactive code, ensuring that your complex observable pipelines behave exactly as expected. Chapter 11, Testing Reactive Code. Introduction: the challenges of asynchronous testing. Writing tests is an essential part of building reliable software. However, testing asynchronous code, especially code that deals with time-dependent behavior, concurrency, and event streams, presents unique challenges. Traditional unit testing frameworks often struggle to simulate the passage of time accurately or manage the non-deterministic nature of asynchronous operations. How do you test if something happens after 500 milliseconds, or only after a button is clicked 3 times in quick succession? RxJS provides specific tools and patterns to make testing reactive code much more straightforward and deterministic. The key is the test scheduler, which allows you to simulate time and observable emissions synchronously within your tests. Marble diagrams, visualizing reactive tests. Before we dive into the test scheduler, we need a common language to describe observables and their behavior over time. Marble diagrams. These are visual representations of an observable sequence, showing values being emitted, errors, and completion notifications along a virtual timeline. They are invaluable for sketching out reactive logic and, crucially, for writing tests. Here are the key symbols used in marble diagrams. Dashes represents the passage of virtual time. Each dash typically represents a frame or a time unit, defaulting to 10 milliseconds in test scheduler. A, B, C, etc., lowercase alphanumeric characters, represent values emitted by the observable. These correspond to values in a companion object provided to the test scheduler. Vertical bar represents the complete notification. The observable has finished emitting values and will not emit anything further. Hash or X represents the error notification. The observable has terminated due to an error. Parentheses groups values that are emitted synchronously at the same virtual time frame. Example: ob means A and B are emitted simultaneously. Caret represents the point in time where an observer subscribes to an observable, used with hot observables. Exclamation mark represents the point in time where an observer unsubscribes from an observable. Example: ABC emits A, then after 20 ms B, then after 20 ms C, then completes after 10 ms. A hash. After 20 ms emits A, then after 20 ms errors. Abc emits O and B synchronously, then after 10 ms C, then after 20 ms completes. The RxJS test scheduler. The test scheduler is a core utility for testing RxJS streams. It provides a virtual, synchronous timeline that you control, allowing you to fast-forward through time-dependent operations. This makes your tests deterministic and repeatable, as you're not relying on actual timeouts. The primary method for using test scheduler is testscheduler.run callback. The callback receives an instance of test scheduler, often destructured as hot, cold, expect observable, expect subscriptions, / conceptual usage, full code and external repo. Import test scheduler from RxJS / testing. Import of, take, map, delay from RxJS. Import operators and creation functions. Import tap from RxJS / operators. Describe RxJS operator tests. Equals. Let test scheduler. Before each, equals. Initialize test scheduler before each test. Test scheduler equals new test scheduler. Actual, expected equals. Assert deep equality of values. Expect actual equal expected. It should map values correctly, equals. Test scheduler dot run, cold expect observable, equals. Const source dollar equals cold ABC. A, 1B, 2C3, const expected dollar equals XYZ. 10 ms delay from cold, then map delay, then first result. Const result dollar equals source dollar, pipe. Map value equals value 10. Expect observable result dollar to be expected dollar x 10y 20z 30 null. Explanation for expected string timing. The string in the expected dollar marble diagram string for map would mean expect observable result dollar to be xyz x 10y 20z 30 if mapping is synchronous and does not introduce delay on its own. The test scheduler dot run function uses a default frame time of 10 milliseconds for each dash. Let's refine the map example's expected dollar marble string to be more precise. If cold ABC means A at 10 ms, B at 40 ms, C at 70 ms, then a synchronous map would emit a map to X at 10 ms, B map to Y at 40 ms, C map to Z at 70 ms. So the expected dollar marble string would be XYZ. Creating test observables. Cold and hot. Within test scheduler dot run, you get access to helper functions cold and hot to create test observables that behave like their real counterparts. Cold marbles values error creates a cold observable. Its values begin to be emitted from the marble string relative to when it is subscribed to. Each subscription to a cold observable starts its own independent execution. Use case. Simulating HTTP requests, promises, or any observable that starts its work on demand. Example, cold AB means 20 ms after subscription, O is emitted, then 30 ms later B, then 10 ms later it completes. Hot marbles values, error, subscription marbles, creates a hot observable. Its values are emitted from the marble string relative to the start of the test. Any subscriptions, character in subscription marbles, will only receive values that are emitted after the subscription point. It simulates a source that is already active, e.g., a button click stream, a WebSocket. Use case. Simulating user interactions, shared sources, or any observable that is already producing values. Example, hot AB means the observable starts emitting at 0 ms. A subscription at 30 ms would receive O at 60 ms, 30 ms after B at 90 ms. Assertions, expect observable and expect subscriptions. These are the primary assertion functions provided by test scheduler to compare your observable's actual output with your expected output. Expect observable actual dollar to be expected marbles, expected values, expected error. Compares the stream emitted by your actual observable with the expected marbles string. The expected values object maps the characters in expected marbles to their actual values. Expected error is optional if the stream is expected to error. Example, expect observable my stream dollar to be AB, A, 10B. 20, expect subscriptions, subscriptions dollar to be expected subscription marbles. Allows you to assert on when an observable was subscribed to and unsubscribed from. This is particularly useful for testing operators like switchmap or takeUntil which manage subscriptions. You get the subscriptions array from cold or hot calls. Example, expect subscriptions, my cold observable subscriptions, to be, meaning it was subscribed at the beginning and unsubscribed at 30 ms. Practical testing examples. Let's illustrate with a few common scenarios. 1. Testing debounce time, / conceptual usage, full code and external repo. Import hot from RxJS / testing. Import debounce time from RxJS / operators. It should debounce values, equals. Test scheduler dot run, hot expect observable, equals. Const source dollar equals hot, ABCDA. Const expected dollar equals E. E is emitted 100 ms after D from D, 200 ms after C. The between C and are effectively 10 ms each. C, 70 ms to 80 ms. E, 90 ms. 100 ms debounce means timer reset after E. So 90 ms at E plus 100 ms debounce equals 190 ms. This would mean E is emitted at 19th dash. So the expected string would be E. The default frame time for a dash is 10 ms. A 10 ms, B 30 ms, C 50 ms, D 70 ms, E 90 ms. Debounce time equals 100 ms, so 10 dashes after E. Thus, total length equals 90 ms plus 100 ms equals 190 ms equals 19 dashes. Const result $ equals source $. Pipe, debounce time, 100. 100 ms debounce equals 10 dashes. Expect observable, result $ to be expected $. Expected string E. Actual correct marble diagram for debounce time, 100 and hot, ABCDE. A 10 ms timer starts. B 30 ms timer resets. C 50 ms timer resets. D 70 ms timer resets. E 90 ms timer resets. After E, 100 ms pass without activity. So E comes out at 90 ms plus 100 ms equals 190 ms. The marble string E 18 dashes before E, then E, represents 19 units of 10 ms. 2. Testing switch map and its cancellation. / conceptual usage, full code in external repo. Import hot, cold from RxJS / testing. Import switch map from RxJS / operators. It should cancel previous inner observable with switch map. Equals. Test scheduler.run. Hot, cold, expect observable, expect subscriptions, equals. Const source $ equals hot, ABC. Simulate inner observables for A and B. Const inner observable 1 equals cold, XY. X at 20 ms, Y at 60 ms. Const inner observable 2 equals cold, Z. Z at 30 ms. When source emits A at 10 ms, it subscribes to inner observable 1. Expected inner values, source ABC. Say, XY starts at 10 ms, emits X at 30 ms, Y at 70 ms. B, Z starts at 40 ms, emits Z at 70 ms. A triggers inner 1, X is at 30 ms. B triggers inner 2 at 40 ms. Inner 1 is unsubscribed, so Y from inner 1 is never emitted. Z from inner 2 is emitted at 70 ms, 40 ms plus 30 ms from inner 2 start. Const expected marble equals XZ, combined output. This defines how the switch map operator will create inner observables based on the values from the source. Const result $ equals source $, pipe. Switch map value equals. If value equals A, return inner observable 1. If value equals B, return inner observable 2. Return of default. To expect observable result, to be expected marble. Expect how inner observable 1 was subscribed and unsubscribed. Expect subscriptions, inner observable 1, subscriptions, to be. Expect how inner observable 2 was subscribed. Expect subscriptions, inner observable 2, subscriptions, to be. This comprehensive switch map test uses hot for the source, simulating an ongoing input. Cold for the inner observables, simulating API calls. Expect observable for the final combined output, and crucial expect subscriptions to verify that switch map correctly subscribed and unsubscribed from the inner observables. Chapter summary, confident reactive code. Testing asynchronous and time-sensitive code is challenging, but RxJS's test scheduler provides a powerful, deterministic solution. By using marble diagrams to visualize your streams, then using hot and cold to define the behavior of your input observables, and finally expect observable and expect subscriptions. To assert the behavior of your output streams, you can thoroughly test even the most complex reactive logic. Mastering these testing techniques will give you immense confidence in the correctness and reliability of your RxJS applications. In our final chapter, we'll discuss best practices, advanced topics, and briefly touch on how RxJS integrates with popular frameworks, preparing you for a productive journey beyond the basics. Chapter 12, Beyond the Basics, Best Practices and Advanced Topics. Introduction, Moving Towards Production-Ready RxJS. Congratulations! You've journeyed from the foundational concepts of reactive programming to mastering RxJS's core observables, operators, and subjects, and even explored advanced testing techniques. You now possess a robust understanding that will empower you to build powerful, scalable, and maintainable asynchronous applications. This final chapter focuses on integrating RxJS effectively into real-world projects. We'll cover essential best practices for memory management and performance, advanced error handling strategies, debugging tips, and a brief look at how RxJS fits into popular JavaScript frameworks. Finally, we'll suggest resources for continuing your reactive journey, memory management and resource cleanup, preventing leaks, the single most critical best practice when working with RxJS, and any event-driven or long-running asynchronous system is diligent resource cleanup, primarily through unsubscribing from observables. Forgetting to unsubscribe from long-lived observables is a common cause of memory leaks and unexpected behavior in applications, especially in single-page applications, SPAs, where components are frequently created and destroyed. When to unsubscribe? Long-lived infinite observables. Always unsubscribe from observables that do not naturally complete, such as those created with interval, from event, or WebSocket subject for WebSocket connections. In components, if you subscribe to an observable within a component, e.g., fetching data, listening to root changes, ensure you unsubscribe when the component is destroyed. Common unsubscription patterns. Manual unsubscribe. Store the subscription object returned by subscribe and call unsubscribe when appropriate. This is often done in a component's lifecycle hook, e.g., ng on destroy in Angular, use effect cleanup in React for manual setup. / conceptual usage, full code in external repo. Import subscription interval from RxJS, class myComponent. Private timer subscription, subscription undefined. Start timer. This timer subscription equals interval 1000. Subscribe val equals console log val. Stop timer. If this timer subscription. This timer subscription unsubscribe. This timer subscription equals undefined. Take 1 for one-off operations. For observables that you only need a single value from, like an HTTP GET request that resolves once. Using take 1 ensures the observable automatically completes and unsubscribes after emitting the first value. Import of from RxJS. Import take from RxJS/operators. This observable will automatically complete after emitting data. Of data, pipe take 1, subscribe val equals console log val. The take until notifier $ pattern. This is the most common and robust pattern for component-based applications. You create a subject or replay subject 1 on your component, which you next, and complete in your component's destruction lifecycle hook. Then all observables within that component can pipe take until this .destroy $. Import subject interval from RxJS. Import take until from RxJS/operators. Class myComponent. Private destroy $ equals new subject void. A subject to signal component destruction. Constructor. This interval will automatically stop when destroy emits. Interval 1000 pipe. Take until this .destroy $. Subscribe val equals console log component tick val. This method would be called by the framework when component is destroyed. ng on destroy. Example, Angular's lifecycle hook. This .destroy $, next. Emit a value to signal destruction. This .destroy $, complete the subject. This pattern ensures all subscriptions are cleaned up reliably without managing individual subscription objects. Importance of share replay for caching and side effects. Revisited from Chapter 8. When multiple parts of your application subscribe to the same cold observable that has side effects, like an API call, each subscription will cause the side effect to happen again. Share replay not only makes the observable hot, but also caches its last values, preventing redundant side effects and ensuring efficiency. Import timer from RxJS. Import tap share replay from RxJS/operators. Const source $ equals timer 0 1000. Pipe. Tap equals console log observable is running. Side effect. Share replay 1. Cache the last value and share the execution. Initial subscription starts the timer and console log. Source $ subscribe val equals console log sub 1 val. A few seconds later, this subscription gets the latest value immediately and shares the ongoing execution without starting a new timer. Set timeout equals Source $, subscribe val equals console log sub 2. Val 3500, performance considerations, optimizing reactive flows. While RxJS is highly optimized, poor usage patterns can lead to performance issues. Avoid unnecessary computations. Place operators that reduce the number of emissions, filter, distinct until changed, debounce time, throttle time as early as possible in your pipe. Chain. This reduces the number of times subsequent, more expensive operators, map, merge map need to process values. Strategic use of share replay. For expensive or repeated observable work, e.g., repeatedly fetching the same data, share replay can prevent redundant execution and improve responsiveness. Minimize side effects. Reactive programming encourages pure functions. Perform side effects, like DOM updates, console logs, analytics calls, only when necessary, often within tap operators or the subscribe block itself. Advanced error handling patterns. Beyond catch error and retry, consider these. Centralized error handling services. In larger applications, you might have a global error service that catch error operators can delegate to. This service could display toast messages, log errors to a remote server, or trigger fallbacks. Circuit breakers. For services experiencing high error rates, you might implement a circuit breaker pattern using retry-when to prevent continuous retry attempts against a failing service. This involves a period of open circuit where no requests are made, then a half-open state for a test request, before fully closing if the service recovers. Debugging RxJS streams. Debugging observable chains can be tricky due to their asynchronous and often complex nature. Tap operator, as discussed in Chapter 7, tap, is your best friend for debugging. Use it at various points in your pipeline to log omitted values, errors, or completion notices. My observable pipe. Tap val equals console log, value before map, val. Map val equals val asterisk 2. Tab. Next, val equals console log, value after map, val. Error equals console error, error in stream, Complete equals console log, stream completed. Subscribe, browser developer tools. The network tab in your browser's developer tools is invaluable for inspecting HTTP requests initiated by your observables. The console tab will show your tap logs. RxJS Dev Tools, browser extensions. While less common or actively maintained than for popular frameworks, specific browser extensions might exist that can visualize RxJS streams similar to marble diagrams during runtime. Check the browser extension stores for RxJS Dev Tools or similar. As of this writing, there isn't a universally recommended, actively maintained one. Integrating RxJS with popular JavaScript frameworks. RxJS often finds its ultimate practical utility when integrated into larger JavaScript frameworks. Angular has embraced RxJS as its primary mechanism for handling asynchronous operations. HTTP client. Angular's HTTP client returns observables for all HTTP requests. Router. The Angular router exposes many events, e.g., route changes, parameter changes, as observables. Forms. Reactive forms provide value changes and status changes as observables. NGRX. A popular state management library for Angular that is built entirely on RxJS concepts, using observables for state changes and effects. Async pipe. Angular's async pipe in templates automatically subscribes to an observable and unsubscribes when the component is destroyed, making template integration very clean. React. While React primarily uses promises and its own state management, e.g., useState, useEffect, RxJS can be integrated. Custom hooks. You can create custom React hooks that manage RxJS subscriptions within useEffect with proper cleanup, like using takeUntilTied to the hook's lifecycle or useObservable libraries. Context API Redux observables. RxJS can be used with context or combined with Redux via Redux observable to manage complex async logic or side effects. Vue.js. Vue also has growing support and community libraries for RxJS. VueRx, a plugin that allows you to easily plug observables into Vue's data properties and lifecycle. Composition API. Vue 3's Composition API provides a flexible way to manage reactive state, and RxJS can be used within setup functions, leveraging on unmounted for cleanup. In all these integrations, the core principles you've learned, observables, operators, subscriptions, remain the same. The framework merely provides the context and specific tools to bridge its lifecycle and data models with your RxJS streams. Exploring further, next steps in your reactive journey, this book has provided a solid foundation. To continue your mastery, official documentation, the RxJS documentation, rxjs.dev, is comprehensive and constantly updated. Community resources, explore blogs, Stack Overflow, and community forums. The RxJS community is active and supportive. Advanced operators, there are many more specialized operators, e.g., audit time, pairwise, group by, window, etc., not covered in this book. Refer to the documentation as needed. Functional Reactive Programming, FRP. Understand that RxJS is an implementation of reactive programming, which is a facet of the broader functional reactive programming paradigm. Exploring FRP concepts can deepen your understanding of why RxJS works the way it does. Contribute to open source. Contribute to RxJS itself or other open source projects that use it. This is an excellent way to learn from experts and solidify your knowledge. Conclusion: the future is reactive. Reactive programming with RxJS offers a profoundly powerful and elegant approach to handling the complexities of asynchronous data and events. By thinking in terms of streams and composing them with operators, you gain unparalleled control and clarity over your application's dynamic behavior. What once seemed like asynchronous chaos can now be orchestrated into a predictable, maintainable, and highly performant symphony. The reactive paradigm is here to stay, central to modern web development. By mastering RxJS, you've equipped yourself with a fundamental skill that will serve you well in building the next generation of rich, responsive, and robust user experiences. Embrace the stream and happy coding.